Hello guys, welcome back to my channel. Okay, so now today I am going to discuss a very interesting topic, that is the toroidal power transformer. Basically, there are various types of transformer being used in various projects, but the toroidal power transformer is commonly used in audio amplifiers and high power linear power supplies. So in this video, I will show you how to model a toroidal power transformer using formulas and some of my analytical thinking about the configuration of toroidal power transformers. And then we will simulate the model in the LTSpice in the last section of the video. So now let's begin. As we know that this is the universal classical equation of the transformers, that is the primary turns upon the secondary turns gives us the turns ratio, and primary turns is denoted by NP, secondary turns is denoted by NS, primary voltage is denoted by primary VP, and secondary voltage is denoted by VS, and so on and so forth. Okay guys, as you can see here. Okay, so after this basic equation, uh, we would be interested in knowing the AC resistance of the copper wire that is being used to wind the transformer primaries and secondaries. So there are two types of resistances, as we all know, that one is DC resistance and another is AC resistance, and the combination of both is known as impedance, whereas the AC resistance is also known as reactance. So the formula is very basic for the inductor AC resistance, that is reactance, which is given by XL equals 2 pi FL. F is the frequency, which is the utility frequency for 230 volt it is 50 Hz, and for 115 volt AC it is 60 Hz. Okay, and L is for inductance. Now another part is the DC resistance. As I mentioned, the DC resistance of the copper wire is not dependent upon the frequency. By the way, the DC resistance is independent of the frequency, and it is only dependent upon the length of the copper wire being used and its cross sectional area. The cross sectional area of the copper wire is basically the the diameter of the copper wire being used. The diameter of copper wire is a standard American wire gauge AWG standard, which I will show you in the next pages of this document. By the way, I have created these documents by myself. If anyone wants this document, just let me know and I would email to them on your email addresses. Okay guys, so DC resistance is dependent upon the copper resistivity. The resistivity of a copper, as we know, it is raw, and it is 16.8 multiplied 10 raised to the power minus 9 ohm meter. L is the length of the copper wire and A is the area of cross section, as I mentioned. Okay guys, so we have learned about AC and DC resistances of the winding of the copper wire. So this is basically the structure of the toroidal transformer, very commonly used. As we all know that there may be multiple primaries and multiple secondaries. So in this picture they have shown two secondaries, that is secondary 1 and secondary 2. Winding of the secondary 1 is this one, and the winding of the primary is this one. As you can see closely that the thickness of the two wires is different. This primary wire is a thin wire, while this secondary winding is a thicker copper wire. So these thick and thin wires varies the inductance values, which we would see in the later section. Right? This is the core, toroidal core, This is the insulation, plastic insulation. The insulation is given so as to ensure that the windings are not short circuited with each other, right? And these are the outlets of the primary and secondary windings wires. I would show the calculation of the case study sample for the Toroid power transformers. Although there are various manufacturers of the power transformers, some are Telema, Multicomp and Toroid, but I would be using the Toroid power toroidal transformer because they have their data sheets in detail specifications. Okay, so this is the AWG chart which I was talking about. So according to the AWG wires, the diameters are change. As the AWG wire number increases, the diameter conductor decreases. This is actually the inverse. So we would see in our sample example calculation where we would be going to use the triad power transformer calculations. Okay, so now moving on to the calculating the inductance of the toroidal transformer for using physical diameters. So actually, most of the transformer manufacturers do not give their technical parameters like inductance, like copper wire thickness and copper wire length being used in the winding of primary and secondary windings. So we can only use our analytical skills and give available data from the manufacturer data sheet. So in most of the manufacturer data sheets, they have given the physical dimensions. These physical dimension, which is usually the inner diameter of the toroidal transformer, the outer diameter of the toroidal transformer, and its height, right? So I was referring to this book in which there is a very unique and interesting formula given about the inductance of the toroidal transformer winding having the rectangular cross sectional area. This I will show you later. Learn this, that this is there are two types of cross section area. One is circular and another is rectangular cross section, right? So this is the formula. L equals means L equals 0.0117 number of turns times square times height of the toroidal transformer times logarithmic of the ratio of outer diameter and inner diameter, and its unit is always in microhenry. Okay, so here is the diagrammatic representation of the physical dimensions of the toroidal transformer. As you can see, h is the height of the toroidal transformer, that is, it is the core around which these windings are wounded around, and this is the toroidal transformer itself, it is a core, and this is the inner diameter, and this one, the bigger one, is the outer diameter. Now calculating the length of the copper wire being used in winding the primary or the secondary. The formula used here are valid for both the primary and the secondary windings. So assuming that the copper wire is winded all over the circumference of the circular toroid, this means that the windings are wounded all over the circular area of the toroid. Okay, this toroid is shown here in semicircle. The rest of the semicircle is not shown, just for you to illustrate the cross section of this transformer inner section. So the winding is wounded all over the transformer. right? And second assumption is that each turn is very close to another turn. That is, there is no gap between these turns. These gaps are shown only to demonstrate you that these are the windings, that is, these are the turns. But in practice, there are not much gap between these turns. They are wounded very close to each other. Every turn is very close to each other. Okay, so the formula to calculate the average circumference of the toroid, that is the outer diameter d2 plus inner diameter d1 divided by 2. This is the formula of average. And we know that the formula of circumference, that is this area only, not the area actually. This is the length. Circumference is actually the length of the circular shape. Pi d, pi times d2 plus d1 divided by 2. Okay. Now in the second step we would calculate the rectangular area of the cross section of toroid, that is this rectangular area, this one. As I have mentioned earlier that there are two types of toroidal transformer, one with the rectangular cross section like this, and another one is the circular one. Like this core is circular, not rectangular, but we would be considering here the rectangular one. Okay, so calculate the rectangular area of the cross section, or in other words calculate the perimeter, rectangular perimeter. The perimeter of a rectangle, as we all know, that its length twice of the length plus twice of the width. This is the formula of the perimeter, twice of the width plus twice of the height in our case. This is the formula for the rectangular perimeter. I hope you guys are understanding my point. We are only considering here the perimeter in order to calculate how much wire is being used in one turn. This is actually one turn. This h plus this width plus this h plus this width, 2 times h, 2 times w makes perimeter of a rectangular cross section. And we would then know how much wire is being used in one turn, and then we would multiply this all over through the circumference. Okay, so the length of the copper wire would obviously be the multiple of this rectangular perimeter multiplied by the circumferential length. That is, if we assume that this circular circumference is a linear line, then it would be simply a multiple of rectangular perimeter. That is, the length of the copper wire is equals to C multiply A, right? This you have to remember, guys. Okay, now calculating the number of turns n. So now basically analytically again, this number of turns n would be the ratio of this circumferential length, that is C, that we have calculated, circumferential length, the average diameter of the toroid into pi divided by the thickness of the wire that is being used. And this thickness is obtained from AWG table that I have already mentioned in previous page. Okay, so now our case study is based on the triad magnetic power transformer. I am considering BPT 48-20830 model. This model is a 1000 VA power transformer and it supports 2 primary and 2 secondaries, and its input voltage can be 230 volt AC when 2 primaries are connected in series, or when 2 primaries are connected in parallel the input can be 115 volt AC. Okay, and its output is at 48 volt AC open circuit in series. That is, when the 2 secondaries are connected in series, you can get a maximum of 48 volt AC, while if the outputs are connected in parallel with each other, then you can get a maximum of 24 volt AC, whereas you can get a high current as high as 41.66 ampere. While in the case of series connected secondaries, you can get a maximum of 20.83 ampere. Okay, this is obvious that when you multiply this voltage with current, you can get 1000 VA. Again, when you multiply this 24 volt with 41.66 ampere, you would get 1000 VA. So the maximum power that you can derive from the transformer secondaries is 1000 VA. So now let's move on to the calculations. Okay, so here is a very important, I got information from this data sheet, that is they have shown that primaries are using the 18 AWG wire gauge wires and secondaries are winded with 12 AWG copper wire. These informations are usually not available in other manufacturers, transformer manufacturers. And this is the schematic of the transformer, as I have mentioned that two primaries and two secondaries, right? So therefore we are given with VP1 115 volt RMS, VP2 115 volt RMS, VS1 24 volt, VS2 24 volt, primary secondaries. I think I hope you guys are getting these points. Power rated is 1000 VA. This I have mentioned already. This means that either this 1000 VA maximum output, right? And our inner diameter for this toroidal transformer is 49 mm. This is this is the data sheet. Just this is the data sheet of the transformer. As you can see here, the inner diameter is 49 mm. This is the inner diameter. This circle which is inside, this is the diameter, that is ID, inner diameter, and this is the outer diameter, OD, and this is height of the transformer. So first of all, we would calculate the DC resistance of the primary winding, and for this we need to first calculate the length of the wire being used in the winding. So in order to calculate the length of the wire, we must first calculate the average circumference of toroid, which I have already mentioned the formula above. All the formulas are mentioned above in previous pages. We just now are putting these values in our formulas to get results. Results are our inductance, primary and secondary inductances, and primary and secondary turns ratio, number of turns. So D2 plus D1 divided by 2. D2 is outer diameter and D1 is inner diameter, right? 178 plus 49 divided by 2, we would get C equals 356.6 mm. Now we would calculate rectangular perimeter. Okay, so how did we know that this triad transformer has a rectangular perimeter, not the circular? This is actually, as you can see here, that height is 76 mm. Its height is 76 mm, whereas if we take the difference of inner diameter and outer diameter, that is 178 minus 49, this is 129 mm, and height is 76 mm, which means this is not circular, because in a circle the diameter is always the same, right? But in rectangular we can have different width and height. So this is the rectangular perimeter. So now rectangular perimeter would be equals to 2W plus 2H. H is already given, and W, here we have D2 minus D1, that is the difference between the inner diameter and outer diameter, divided by 2. Divided by 2 here because this is because here if we minus d2 from if we minus d1 from d2, we would get this distance and this distance. So we do not want to take it twice, we only want only this distance, so we would divide the value by 2, right? So we would get W equals 64.5 mm. Just put these values in the formula and we would get A equals 287 mm. So now lastly we would multiply C with A as I have already mentioned in the above formulas, and we would get the length of the copper wire that is wounded around the entire toroid for the primary winding, that is 102 meters. So the copper wire of 102 meters in length is wounded around the toroidal transformer as a primary winding. Correct, right? And this is just for the sake of your simplicity and just for your sake of understanding that I have shown here the realization of the circular toroid in a linear form. That is, if we would have opened up the toroidal transformer into linear form like in a lengthwise, then it would be a 356.6 mm long and its A value is 287 mm. This. Okay, so now moving to calculate the area of the cross section of the circular copper wire AWG. Okay, now we are going to calculate the area of cross section of the wire, that is the copper wire being used here. AWG 18 has the diameter of 1.023 mm. You can check this in the AWG table available very easily online, or you can ask me. I will send this document to your email addresses, whoever wants it. So now we would simply place the values in the formula. L we have calculated 102 mm, and rho, this is the resistivity value we will place in the formula, and this is the area of cross section of the wire, that is 1.023 mm square d square divided by 4 this. So we would get the DC resistance of the wire of the primary winding as 2.13 ohm, right? So this is very plausible, very practical value. R equals 2.13 ohms, right guys? If you guys have any question, just let me know in the comments and I would answer every question. Now we calculate the primary winding number of turns. Number of turns is again depicted through analytical consideration, like average circumference of the toroidal C. This C, you guys just know that this C is the realization of the circular toroidal being opened up in a linear space, in a linear fashion, and we know that the turns are wounded on the copper, on the transformer core, very close to each other. There is no gap between them. So actually the diameter of the wire itself determines how many turns are there in the core. That is this thickness of the copper wire. This is the diameter, and this is the length. This length divided by this thickness of the copper wire determines the number of turns, right? This I have evaluated through my analytical consideration. So we would get this value 356.6 mm we have calculated above C, and AWG American wire gauge number is 1.023 mm for AWG 18, and we got 348 turns. So now this is very simple. Now we would simply place the values of number of turns and height of the toroidal transformer, as we know it is 79 mm, and D2 and D1 178 mm, 49 mm, and we would get the inductance, that is 62.7 microhenries. Isn't it cool, guys? I can tell you with surety that most of the students get confused in getting and in evaluating this inductance formula, and they usually don't know how to calculate the inductance of the primaries and secondaries, but they know the ratio of the inductance, they know the ratio of the turns turns, but they don't really cannot get this value. And I would place this value in the LTSpice simulator and show you how this would work. Now we calculate rest of the parameters. Now we would simply use our transformer classical equation and put our values. You can see, guys, we get 72 turns secondary, and we get 2.73 microhenry as our secondary inductance, right? So we have got secondary turns, secondary inductance, and we here got secondary primary inductance and primary turns, right? So that is it, guys. This is it. Now we move on to our simulation. Here in our simulation I have already placed the schematic and already placed the inductance values in primary and secondary, right? And this resistor I have placed here only for the sake of simulator, because simulator gives error whenever you do not have any resistor placed in series with the source and with the primary inductance. This is important for only for the simulator, and just do not uh, make this resistance 1 ohm or 2 ohms. This would be very high and it would dissipate voltage across it. So just keep this value as low as possible. I have kept it 0.01 ohms. So now let's simulate our circuit. This is our input. Okay, so I forgot to mention here that I have used 115 volt AC, and which is 162.61 volt peak. Here in LTSpice, the voltage source, it has the option of amplitude. It does not have the option of RMS. So I have manually converted it into voltage peak. Peak voltage is equals to under root 2 times VRMS. So under root 2 is 1.414 multiplied 115. So it is 162.61. And here I have placed 162.61 volt at 60 hertz, right? 60 hertz. So I have placed two grounds also here, as we know that the transformer primary and secondaries are isolated with each other, so their ground should be separate. This is the separate ground, this is the separate ground for primary and secondary. So I would take this point as the reference point and I would see here what is our secondary output. And boom, here is our secondary output. This is around 31.76 volt and our primary is at 162 volt. So if we calculate the voltage ratio, 162.61 divided by peak 31.2, this is 5.2. that is our turns ratio is coming out to be 5.2. okay, while from here our turns ratio we can calculate 62.7 divided by 2.73 square root 4.79, that is around 5, 4.8. Right, guys, so this is something we calculated from our calculations, and simulation results are showing something around 5. So turns ratio is nearly the same with our calculation and with our simulation. So I hope guys you liked my video, and please do subscribe to my channel and like my videos, and share it with your friends and within your community so everyone can get benefited from my videos. Thank you.